All right, so welcome back again to week 8. So we're going to be talking about graph coverage for source code tonight. Last week we looked at graph coverage. We talked a bit about node coverage, edge pair coverage. We talked about prime paths. Tonight we are mostly, I won't go as far as to say only, but mostly going to be talking about data coverage that we introduced at the end of last week. Where we have defs of variables and then uses of variables and the different paths between them. Assignment 4 is due tonight under our new assignment grading scheme that's due at midnight, or I guess before midnight. As long as it has a 10/17 date on it, you're on time. Assignment 5 will go live. I think it appears after this class is over, so 7 o'clock tonight. Assignment 5 is based on our graph coverage content, and we've got 3 weeks out to do that, so a little more time than the last couple, which have been every other week. Any questions on the schedule or syllabus or any of the other kickoff stuff here tonight? All right, then let's launch into a look at our quiz. Nope, not that. Is quiz. All right, quiz 7 review. Overall, really good results on this quiz. Lots of 10s and 11s, so nice work. I do find it interesting. I compare these from semester to semester just to see if the trends kind of look the same. Right, this class is a bit bigger than what I've done in the class, but does the spread of grades look the same from quiz to quiz? And it's kind of remarkable how similar they are from quiz to quiz. So I guess that's good feedback to me for which are too easy, which are too hard, which are just right, or whatever. But this is just about exactly the same distribution from a year ago. Okay, so this quiz had 8 different graphs. You got one of these at random. They're all pretty much the same, but just a little bit different. And then they had the same questions, regardless of which graph you got. So I've highlighted 2 of them here, and this set of slides contains the correct answers for these 2. I'm not going to go over both of these, but I will go briefly over the first one just so that y'all get a feel for it. Of course, recognizing that there's a 7 out of 8 chance that you actually had a different quiz and that these won't be your particular answers. And then, of course, the correct answers for your graph should be visible on your on Blackboard in the quiz itself, and if they're not, let me know and I'll see what I can do to fix that. All right, so we had a graph, we've got nodes, we've got edges, blah blah blah. We come up with this graph. So what are all the nodes that can be reached from node 3? So this does not need to be direct. It's just, if I'm at node 3, where can I go from here? 3 is one of them, because with a path of length 0, I can reach node 3. That's a little bit picky, I guess I'll say. So while 3 is technically in this list, you were not graded down on the quiz if you did not list that a node can reach itself by not going anywhere. But other nodes that we can reach on this graph, we can get to 5 and 6 and 8 directly, and then we can also get to 7. So 5, 6, 7, 8, and 3. Is 14136 a test path? Let's see, 14136 starts at an initial, ends at a terminal, has branches all along the way. No, that's 8. Okay, so that's how easy it is to get it wrong, because watch me. 14136. No, that's not a test path. It doesn't end at a terminal node. 14138 would be a test path because it does end at a terminal node. How about 1, 4, 1, 2, 1, 3, 5, 7, 8? 1, 4, 1, so far so good. 2, 1, so far so good. 3, 5, 7, 8. Yep, that looks like a test path. We've got edges all along the way in order. We started an initial, ended a terminal. How about 1, 3, 1, 3, 5, 7, 8? 1, 3, 1. Well, I can't go from 3 to 1. No edge there, so that's not a test path. What are the requirements to satisfy edge pair coverage? I'm not going to go through each of these because there's a fair number of them, as you can see, but basically we want to make sure that we're not only following the arrows in the obvious way, but we've got, so for example, we have 1, 2, 1 as an edge pair. We also always want to remember that we have the opposite, right? We have the inverse of that as well. Anytime we've got a loop like this, we've got 1, 2, 1. I apologize if I misspoke a moment ago. It's 1, 2, 1. But then we also have 2, 1, 2. It's easy to overlook those, but you want to always make sure to remember, if I've got a loop in one direction, 1, 4, 1, then 4, 1, 4 is also a test path. So things to look out for, loops, like I said. Also, in a graph like this, crossovers are kind of interesting. And I'm putting that in quotes. It's not really a term, it's just a word that I'm using. But what I'm talking about there is 2, 1, 4 and 4, 1, 2. So we're not just even only in the loops over here, but we can actually cross back and forth from side to side, at least according to the graph syntax. So given those test requirements for edge pair coverage, let's try to satisfy them with test cases. And here's a potential answer. There are, I don't know that I would be willing to say an infinite number, but well, I guess there's a loop involved. So yes, by definition, there are an infinite number of test paths that we could select to satisfy this. My usual approach here is I'll just start someplace. 1, 2, great. What do I want to do from there? Well, I can only go back to 1, so that gives me 1, 2, 1. So I'll highlight this blue one right here, 1, 2, 1, and then I'll say, what can I do next to grow my coverage? Well, I can go 1, 4, 1, and that'll grow some coverage, and then I can go 1, 2, 1, 3, right? That takes care of 4, 1, 2. So wherever I have ended up, as I'm building my test path, I kind of look for, okay, what's the next thing I can do out of my list of test requirements to capture something else? That's kind of, a greedy algorithm approach to doing this. What's the most additional test requirements I can get next based on where I am? It's certainly not the only way to do it. I find that a very intuitive way, which is why I'm mentioning it to you. You don't need to do it that way. But then when I finally work my way down and get to 8 in my first test path, then I look at what's not covered yet. And I haven't covered 1, 3, 8 or 1, 3, 6 or 6, 7, 8. So, okay, we'll figure out with my next test path, how can I get 1, 3, 6 and 3, 6, 7 and 4, 1, 3, and I'll try to work my way through that. And then 1, 3, 8 is the thing that remains after that. So I need a third test path to capture that. And like I said, many other combinations are possible. If I don't mention it today, in part of our exercises today, I'll be talking about minimal test paths. And if I guess I'll define that now, and if I don't redefine it, if I don't explain it again later, just point that out to me because I want to be sure I mention that. A set of minimal test paths is not necessarily the smallest possible number of test paths that are necessary. What it means is non-redundant test paths. A minimal set of test paths is a set from which, if I remove any of them, I no longer have complete coverage. So this is a minimal set because if I remove any one of these 3 test paths, I no longer have complete coverage. And I think it's also a minimum set, meaning I can't do it with fewer than 3. But I could do it with 4 or maybe 5 and possibly still have a minimal set such that if I took one away, I don't have coverage anymore. So when I'm asking for a minimal set of test paths, I don't necessarily mean the smallest number of tests possible. I mean that your set is non-redundant such that you can't take anyone away and still be able to achieve complete coverage. So remind me of that again later if I don't mention it. So what's the length of the longest prime path, and give an example? Well, there are four, at least that I've found in here. And recall, a prime path is a simple path that can't be made any longer by extending it on either end. And a simple path is a path that does not contain a loop, although the path itself overall could be a loop. So for example, 2, 1, 4, 1, 2. I need to rephrase that definition. What I meant to say was, a simple path is a path in which no node appears more than once, except that the first and last node can be the same. So the path can't contain a loop or part of a loop, but it can in its entirety be a loop. So 2, 1, 4, 1, 2 would not be a simple path because 1 appears twice. 1, 2, 1 would be a simple path. Even though 1 appears twice, it appears at the beginning and at the end. And so that would be the longest prime path, because if I went 1, 2, 1, 3, that would be the longest prime path that I could make out of that. That is, I couldn't make that simple path any longer and still be a prime path, because if I went 1, 2, 1, 3, then 1 would appear twice, but not at the beginning and the end. So given that, if we go through this graph, we end up with length of 5 for this particular graph with these four particular choices. So things to think about: prime paths are not necessarily test paths. So 1, 3, 5, or 6, 7, 8, that is a test path, and it is a prime path, but it's not the longest prime path, because I could have started that at 2 or 4 and gone, for example, 4, 1, 2, or 1, 3, 5, 7, 8, and that would have been a little longer and would not have been a test path. And prime paths don't need to be test paths. Okay, and then we can do the same thing all over again for another graph. I'll leave that for you to look at if you want to investigate that further, but I am not going to go through all those details right now because we have many other things to do tonight. All right, where's our house cup? So kudos to the Gryffindors, who have kind of been lagging behind a little bit in the first half of the semester and are now right back in the game. But we got to watch out for those muggles. I mean, they're the ones that aren't supposed to be magical, but they're just kind of steadily creeping ahead just a little bit. So good job, muggles. And actually, again, this is something I do every semester, at least since we've been online. I think this semester is probably just about the closest at this point of the semester. Previous semesters, it's usually been pretty obvious which 1 or 2 teams are going to be in the running. And here this semester, still, you know, it's an open game. Could be anybody. All right, so any questions about that quiz or graphs or prime paths or anything related to that we want to talk about before we move on? All right, then next up, we'll take a quick look at assignment 3. All right, so assignment 3 has been graded, everything's posted. And, you know, this was not a particularly difficult assignment. It was really just a matter of taking those things we had already talked about in class and claim class exercises and turning it into an actual implementation. And so good work, everybody, on, you know, getting a good implementation in there for assignment 3. Not too much else to talk about here, since, you know, everybody's approach Every group's approach could be different. We certainly can't compare one to the next because you had a lot of freedom to do whatever you wanted here. But here was the grading guidance. This also appears in Blackboard so that you can see what the specific expectations were and what they were worth. All right, that wraps up for assignment 3. So then if we're ready and don't have any other questions we want to deal with first, then we'll move on to tonight's content. All right, let's go. We're going to do tonight just a little bit differently. It's kind of midway between what we've normally been doing with lecture and class exercises and what we did 2 weeks ago, where we spent the whole class in an exercise. This one, we're going to go through a little bit of a lecture, and then we're going to go through a pretty long collaborative exercise that, I'll be driving, and you all have an opportunity to contribute answers to what we should be putting in. And we're going to go through that because it's relatively complex and more complex than I'd like to kick out to each of the groups individually. And then we've got some smaller group exercises at the end. So we are still here in graph coverage, and this week we're really going to be specifically talking about applying that to source code, and in particular applying data flow criteria to source code graphs or source code derived graphs. So what's our overview? We very often, right? It's very, very common to apply to take program source code, turn it into some kind of graph model, and apply graph-based criteria to that to generate tests. And when we're dealing with source code, the graph is almost always the control flow graph of the source code itself. So this is very low level, right? We are building our testing and building our test requirements directly based upon the implementation. So we would call that very much a white box testing approach. And we talked about a few things last week. We talked about node coverage, which requires the execution of every statement, where statements from the source code are kind of conglomerated into nodes, where the maximum number of statements that don't have a decision in it get kind of crammed together and put in one node. We had edge coverage, or a few varieties of edge coverage, right? We had edge coverage and then edge pair coverage, where we require execution of every branch or every pair of sequential branches or edges in the graph. And then at the end of the day, at the end of the lecture yesterday, last week that is, we talked about data flow coverage, where we take the control flow graph, we augment or annotate the control flow graph with the definitions and uses of various variables, and then use data flow coverage criteria to come up with a set of test requirements based on how those variables are being used. So 3 different ways, related, but different ways that we can use graphs to generate test requirements. So let's talk a little bit about control flow graphs again. The control flow graph is really just a model of the software with respect to what the control flow structures are. So where are the loops? Where are the if statements? Where are the decisions? All right, if we had a method or function that had no decisions, it just did a bunch of math, that might just be a simple node, right? No matter how many lines of code I have, if I just run this, then this, then this, then this, then this, it doesn't matter how many they are, that's one node with no decisions, so no branches. So nodes contain statements, a statement or a collection of statements, a basic block, right? That's a collection of statements with no control flow in it, such that if we execute the first, we execute them all because there's no way out. And then an edge is some kind of control decision, an if statement, a case statement, a while statement, something like that, where a decision gets made that redirects the control flow. And we can take those control flow graphs and we can annotate them with various kinds of extra information. And last week we did a lot with annotating control flow graphs with the source code, but we can also, as we at least touched on last week, annotate the control flow graph with the definitions of variables and the uses of variables. So what's that going to look like? Well, it will look like these graphs, right? If we have, if x is less than y, then y equals 0 and x equals x plus 1, else y is equal to 0. So we have our if statement here. If x is less than y, we come down to node 2. We've got the statements in node 2. Else, we have node 3. And then those will come together again in this for, which perhaps contains more code after this. Perhaps there's a return statement. I've drawn this as a terminal node, and maybe that's not quite justified because the code here doesn't really tell us what happens next. We can also have an if statement instead of an if-then statement. An if statement, if it's true, we have a node with some more statements. If it's false, we don't have any statements. We just kind of flow through until the control flow comes back together again. Now, my slides, for the most part, and the textbook are annotating decisions on edges instead of on nodes. So what you'll see here is very much like what you'll see in the book. That this node is really if x is less than y, but we choose to annotate those things on the graph edge instead of on the node. We could take a different approach. We could annotate the node with the decision, right? We'll take the node, we'll put if x is less than y, and then we'll label the edges as true and false. From a control flow graph perspective, this is perfectly valid, right? It's a perfectly adequate way, it's just an alternate way to do it. But it does bring up a couple of questions. And I already had one discussion here in the Blackboard forum, but I posted a question or started this discussion yesterday on Blackboard, or maybe it was this morning. It all runs together. What's the difference between these? And are there any implications? If I annotate my edges with the variables versus annotating the node with the decision statement, does that change the graph? Or does it, well, it doesn't change the graph. Does it change the test requirements? Are there any implications? Does that cause me to do anything differently? And I'll say that for quite a while, a couple of years that I've been teaching this course, I felt like, yeah, you know, really there's no difference between these two. They're exactly the same. And it was actually just over the weekend as I was preparing this content and going through the content that I finally realized, you know, there is a very subtle difference between these two and their effect on test requirements. And so we won't have that discussion here, but I'd love to hear what you think and see if you have any insight into how these two actually are different with respect to requiring particular tests. So let's talk about that on Blackboard. All right, so a couple of examples of components that are, or software features and what they look like in a control flow graph. We can have an if return, right? This is not an atypical structure, right? I'm in some function, and if some condition is true, then return, otherwise go on and do some other things and eventually return. And that gives us a graph that looks like this. We now have two terminal nodes because we have two returns. And this return is a different statement than this return. So it goes in a different node, right? Reaching this return statement is executing different code than reaching this one. So we have a structure like this. What if we have a while loop? While loops can get a little bit complicated because while loops force us to bring in dummy nodes, right? Nodes that don't really, aren't really reflected in the code. So for example, if we have a while statement, we first have this first part of, we first have the initialization here that comes before, right, x equals 0. And then we have our while loop. And if we're annotating the branches, then there actually is no code here in node 2, but we have to be able to get back up here to do this comparison again. So we've had to insert this dummy node here that does not actually represent a specific statement or a basic block, assuming again that we've chosen the textbook approach to annotating the edges with what the decision code really is. Now, a for loop is perhaps even more interesting because a for loop forces us to break things up a little bit more. So in a for loop, we have this one statement, but this one statement has an initialization piece, a comparison piece, and an increment piece. And those actually will get split up into different places. So we actually need a new node for this initialization of x equals 0. And then we've got our dummy node where we are doing the test, right? The test happens in the outgoing edges. And then we do whatever is within the an emergency notification that I don't care about. Okay, safely ignore that. Of course, both phones are doing it simultaneously. Okay, quiet. Sorry about that. If your phones haven't gone off, I'm sure they will shortly. Okay, so we've got our initialization node. Then we've got our dummy node. Oh, stop it. Can't you see I'm busy? We've got our initialization node. Then we've got our dummy node. Then we have the node that contains whatever the code is that's inside the for loop. And then we have the node that contains what the increment action is. And then we go back up again and go back into our comparison. Now, we could do a couple of things here. We could combine nodes 3 and 4 because really this is a basic block. If I execute this statement, then I'm going to execute this increment. So I could combine those two nodes and take this one off the graph and put x++ up here. That would be a logically perfectly good thing to do. You'll see that it's often drawn out this way, and the textbook usually draws graphs out this way to just make it clear that this node down here, node 4 with this increment, that's actually part of the loop itself, right? Part of the control itself, the for loop itself, not part of what happens inside the loop. Likewise, we could combine this initialization with whatever came before, right? Whatever lines of code might be up there. But we will often separate it out so that it becomes clear that, oh, that's not just some code that's being executed, that's part of the for loop. Okay, what about a while loop? Well, while loop has a little bit of a different structure. While loop being a post comparison, right? Where our for loop is a pre-comparison, it does the test, or pre-test does the test before it executes the body. A while loop executes the body at least once before it does the test. So here we've got our initialization line, followed by the body of our code. So here, this is no longer a dummy node. We're actually executing the body of the code here, right? The body of the while loop. And then we have the edges where we do the while loop test. And if that's true, we just loop back into the same node because then we'll execute the body contents again. And if it's false, then we bail out of that loop and go on to our next content. Now, things like this, control flow graphs like this, they can start to get pretty complicated. And when we start using things like break statements or continue statements, we're really driving up. It's a little bit ironic, right? Because we're using those things to try to simplify our code. And I would argue they do simplify our code and they make it easier to understand our code, right? I say, okay, we get to the break, great. I skip over the rest of this. I just go into the next iteration of the while loop. That's very clear to us as programmers. But it actually drives a fairly complex control flow graph. So we initialize X and then we do our while loop. And if it's true, then we come down here and we do y equals f of x, and then if y equals 0, we break. Well, what does break mean? Well, break really means we get out of the while loop entirely, so we have to jump away from that into what comes next, which is the return. Whereas if I do a continue, then I skip over what's next, but I jump back into the loop again. So they do get a little messy, but maybe not as messy as exceptions, which we'll see in a moment. How about switch statements or case statements, if you prefer? Those are usually fairly straightforward. We basically have one node where we're making the decision. So here we have a node where we're doing the read, and then we have our branches where we're coming out and we have one branch for each of the possible cases. And then typically, if we have break statements, we'd all fall together again at a node afterwards that would collect it all. However, if we are missing a break statement or have not put in a break statement, I don't want to say missing because that implies it's accidental. If we don't have a break statement, then we fall through to the next case. So if C equals N, I come over here, I set Z to 25, but because there's no break statement, I go right on over here and set X to 50, right? I flow right into my next case. And then finally, we've got exceptions. And exceptions really get to be a mess. Exceptions are a mess if we're doing the catching locally, and they're even more of a mess if we're doing the catching remotely, right? If we're throwing the exception and then backing out right to the caller and catching it in the caller, then the control flow graph really becomes kind of ugly to deal with. So this is something that, compilers are doing this. Compilers are building these control flow graphs. But it's kind of hard for us as developers to accurately get our heads around it when we're doing things like exceptions. They can be difficult. All right, so let's look at a specific example. Here we've got this piece of code, compute stats. So compute stats is going to take an array of integers, cleverly called numbers, and it's going to do a bunch of things. It's going to compute the mean, it's going to compute the median, it's going to compute the standard deviation, and then it's going to print it all out. So let's turn this into a control flow graph. All right, question in the chat. If we call methods inside branches, are we treating methods called as normal statements, or are we developing subgraphs? So that's a great question. And I think the answer is, well, it depends on what you want to accomplish. Normally, I would say that if you are trying to do graph coverage, edge coverage, node coverage, data flow coverage on a particular method, you could treat a function call or a method call, you could treat that simply as a line of code and build it in. So it appears in a node by itself or with other things in its basic block, right? It's just another line of code. The fact that it itself has its own logic is probably a case to be dealt with in its own unit test that deals with that method, where we would then graph out that whole method. Because if you took your control flow graph and tried to include in that everything that you called, so I've got a graph and it's got subgraphs all over the place, I think that would quickly get out of control. So I think I would normally not take that approach. All right, so we've got back to compute stats. Let's build ourselves a control flow graph. We're going to start off with our entry point, right? So we get called, the method gets called, so we've got our little incoming arrow. We've got our first node. This is a basic block, so we're going to set length equals to whatever. We're going to define things. We're going to set num equal to, or sum equal to 0. And now, for convenience, because I want to keep the graph a little bit smaller because I only have so much real estate on the slide. And if I break everything out into more nodes, then it gets so big that I have to shrink it and we can't read it anymore. So in this example, I'm going to take this for initialization and I'm going to include it in this prior basic block. This is legitimate. It's a reasonably correct thing to do, because if I execute this code up here, I am definitely going to execute initializing I. There is no question about it. So it is okay to put it in the basic block. Then we're going to have our We're going to have our length comparison, whether I is less than length. Again, taking the textbook approach, I'm going to create myself a dummy node that has no basic block in it. And I'm going to annotate the branches with that condition and the inverse of that condition. Now we get down here and we're in node 3 where we're going to say sum plus equals numbers. And again, for convenience and for keeping the graph small, I'm going to include the increment into this basic block instead of just chaining down and having another basic block. And then we head back up to node 2. And then when I is no longer less than length, we fall out of that. We get into a basic block that sets median and mean and var sum, and again initializes I, included in the block for the same reason I talked about. Then we have another loop, functionally the same loop, right? From I for I equals 1 to length or less than length. So that looks just the same. Then we have some different code that we execute within the loop. We set var sum, and then we'll increment and come back again to execute the loop again. And if the loop condition is no longer true, we'll drop out of that, and then we'll do all this other stuff and then return. So this is a terminal node. So that gives us a fairly nice, clean graph to work with. So what are our edge coverage test requirements? Well, we have 1, 2, 2, 3, 3, 2, 2, 4, right? We can make that list of test requirements. We can use that to then build up edge coverage test paths. So again, kind of taking that greedy algorithm, I'll start with 1, 2, because of course that's the only thing I can do. What should I do next? Well, if I go to the left, I'll get more nodes than if I go to the right. So I may as well go to the left and go to node 3. That gives me edge 2, 3. From there, I have to go back to 2. That gives me edge 3, 2. From here, I can go to 4, giving me 2, 4, then 2, 5. I'll apply the same logic again. So I'll go to 6, giving me 5, 6, then 6 back to 5, and then 5 to 7. There's my first test path. And in fact, I've covered all the edges. So I can achieve edge coverage on this graph with that one single test. What if I want to do edge pair? Well, here's my edge pair test requirements. So I'll take that same basic approach. I'll start someplace, and let's say I'll start 1, 2, 3. Why not? So we'll go 1, 2, 3. Now, where can I go next to get an additional edge pair? Well, in this case, there's only one place I can go next, which is back to 2. But conveniently, that gives me edge pair 2, 3, 2. If I want to maximize my edge coverage, I can go back to 3 again. And that gives me edge pair 3, 2, 3. From there, I have to go back to 2. And that doesn't give me anything new, right? Because now my current working edge pair that I've just executed is 2, 3, 2. I've already covered edge 2, 3, 2. So this particular edge that I just took to go back to 2, that did not increase my coverage in any way. And that's okay, perfectly normal. From there, I'll go to 4. That gives me 3, 2, 4. Then we go to 5. We'll go through 6, back to 5, back to 6 again for the same reason that we had in the above loop. Have to go back to 5. That doesn't increase my edge pair coverage. And then we go to 7. So that gave me a lot of the edge pairs, but I've still got 2 hanging out there. So we need another test path, right? This test path, or a very similar test path, covered all of the edges, but it didn't cover all of the edge pairs. If I want to cover edge pair, I need at least one more test path. I need to get 1, 2, 4. And from there, I can go to 5, which doesn't give me anything new. But then I can go to 7, which then covers 4, 5, 7. So now those 2 test paths have covered edge pair coverage. If I want to do prime path coverage, I'm going to breeze through this one a little quicker, but here are the prime paths that I need to cover. These are my prime path test requirements. But I'm going to basically take the same approach here. I'm going to take a greedy approach. I'm going to capture all the ones I can with the first test path. Then I'll take another test path to capture some more, and I'll just kind of continue capturing whatever I can until, in this case, now with 4 test paths, I've satisfied prime path coverage. So you can see, I think, from this that edge coverage is possibly more thorough than node coverage, and edge pair coverage is more thorough than edge coverage, and prime path coverage is potentially more thorough than edge pair coverage. At least in this case, it took more tests. So I'm doing more work, but I'm also perhaps finding more defects. I'm at least giving myself the opportunity to find more defects. All right, so let's switch over and talk now, go back to the end of last week and talk about data flow coverage. So we touched on these briefly last week. We've got defs and uses. A def, or definition, is a location where we're taking a value and we're storing that value in memory. So what does that mean? What is a def? Well, the most obvious def is anything where I have an L value, right? I have a variable on the left side of an assignment. In this case, x equals 44. I just defed x. But there are also some slightly more subtle ones. So for example, if I have a variable that's an actual parameter in a call, and the method that I call changes the value, and changes it in such a way that I see the changed value, right? So we're talking from a CS compiler perspective, we're talking about things that are called by reference, not called by value, right? Because any variable that's called by value, that change doesn't come back to me. But calling something and passing it by reference, that does come back to me. So if I put a parameter on the parameter list of something that I'm calling, and the value of that parameter is changed in a way that I will see the change, then that's also a def. And on the other side, on the side that's called, right, the method that's being called, a formal parameter, right, the parameter list at the start of your method, that's a def, because that call is setting the value for you. Then we have uses, and a use is any place where we're accessing the value of some variable. So obviously, anywhere where it appears on the right side of an assignment, right? X equals y plus z. That defed x, but it used y and z. Anywhere where a variable appears in a conditional test, that's a use. Anywhere where a variable is an actual parameter to a call. If I call some sub function, right, some sub method, and I pass a value in, that's a use of that variable. Anywhere where I am using a variable as an output, return x. If I say return x, then that is a use of x. And if I say print x, that is a use of x. So I guess I got those two backwards, out of order. All right, so now let's get into a couple of definitions. We can have first a DU pair, or a def use pair. A DU pair is a related def and use, where starting at the def, we are able to get to the use. We're able to work our way through the graph and reach the use. A DU pair does not need to be def clear. What's def clear? Def clear means a path from a def to a use that doesn't redef it along the way. So if I def x and then use x, that's a DU pair, and it's also def clear. But if I def x and def x again and then use x, that's still a DU pair from that first def to the last use. But it's not def clear because there was another def in the middle. So that brings us to another definition, that of the DU path. And a DU path is a simple path. Okay, so remember, a simple path does not have a loop in it, although it can itself be a loop in use entirety. But a simple path from a def to a use that is def clear. So if we have def of x, use of x, that whole thing is not a DU path because it's not def clear. But the subpath from the second def to the use, that is def clear. So that's a DU path. So what about defs and uses that happen in the same node? So a def and a use in the same node are a DU pair only if the def comes after the use and the node is in a loop. So if we have here y equals x, that's a use of x, and then x equals y plus 1, that's a def of x, and then it's in a loop, so this def of x can come back around and get used here. That is a DU pair. But it's not a DU pair if in the same node the def comes before the use. So we def x and then we use x. That is not a DU pair. That's called a local use. And so we don't care about that from the perspective of data flow modeling, because obviously, if I execute that node at all, then I've executed the def and the use, right? So I don't need to worry about I don't need to worry about managing any kind of DU path, right? So I can ignore those. That's not, we don't consider that to be a DU pair. All right, so here's where we kind of get into our big collaborative example. We're going to go through a fairly detailed, fairly large and fairly detailed example of working out everything that goes with data flow criteria and defs and uses. So your contributions to this by voice or by chat, either way, are welcome. In fact, please help. All right, so we're going to go back to compute stats. We've got compute stats right here. We've already done our control flow graph. Here we've annotated the graph with the source code. We could, if we wanted, highlight the color coding just to make it really obvious where all the pieces of the defs, or excuse me, where all the pieces of the source code fit on the graph. All right, then our next step is we're going to take that source code and we're going to convert that source code into annotations of defs and uses. So let me back up a second here. If we look at node 1 set length, and it set sum, and it set I, and it used numbers, right? Numbers here is an R value on the right side, so that gets used in the course of setting length. So the things that are deft at node 1 are numbers, because numbers was an actual, was a formal parameter. So numbers gets deft, sum gets deft, length gets deft, I gets deft, and numbers gets used in the course of setting I, or setting length. And we can repeat that and set up defs and uses on all of our nodes, and importantly, on our edges. So if we go back here and look at this edge, I is less than length, we're going to annotate that and say, well, the use of this edge, so we're notating that 2, 3, that says it's an edge rather than a node. The use on there is I and length. We're not changing anything, but we're comparing I to length. So both of those variables are used. Now we have one other little trick going on here. We have a loop here that's using I. Again, I'll go back to the source code for a moment. We have a loop here that's using I. And we have a loop here that's using I. Those are two different variables. If we look at I is being declared inside the for loop. So these are scoped completely differently. This I up here has nothing to do with this I down here. They are totally different variables. So a convenient thing for us to do to help us remember that is to just take one of them and rename it. So here, for this second loop, I've renamed I to be I2, because I don't want to mistakenly fall into the trap of saying, oh, hey, I got deft over here and then it got used down here. No, it didn't, because those are two different variables. I can't get used outside of this loop because it goes away. So this I is a different one. So I've renamed it. So now we've got our tables. So we set these tables up. We've got our nodes. We're going to just document what the defs and uses are for each node and what the uses are for each edge, noting that while we can have uses on an edge, we can't have defs on an edge, right? Because anything that would be a def would appear in a node. There might be an exception to that statement, going back to Juan's question about calling submethods or subfunctions, but we're going to skim over that for the moment. All right, so let's work on filling this in. And to work on filling this in, I'm going to make it easier. I'm going to go one line at a time so that we can see the graph. So what are our defs and uses for node 1?
Defs are numbers sum list I, and uses are numbers.
Great. This part of the process is not the hardest part of the process, right? So there we go. Our defs are numbers, sum, length, and I. We just stole that right here off the annotated control flow graph, and our uses are numbers. If we go to node 2, what are our defs and uses at node 2? I'm going to take that silence as you all being very clever, because in fact there are no defs or uses at node 2, right? There's no code there. That was a dummy node for our loop, and the control flow graph didn't get annotated there. So no defs, no uses for node 2. How about node 3?
Defs are sum and I, and uses are sum, I, and numbers.
Exactly. All right, and we're going to continue through this. I think we won't beat this too hard, right? We get to node 4, we've got our defs, we've got our uses. We get to node 5. We already fell into this trap once. Now we know there's no defs and uses there on node 5. Node 6, defs are varsum and I2 and uses these. Node 7, defs a few and uses actually quite a lot. Now we need to go to edges. Edges 1, 2. What's deft or used on edge 1, 2?
Nothing.
Nothing. Exactly. That edge doesn't have any annotation, nothing going on there. Now we get to 2, 3. What's deft or used on 2, 3? Well, obviously there's nothing deft, right? We can't def on an edge, but we can use on an edge. Yeah, I and length. Yes, exactly. We've got I and length used on edge 2, 3, and not surprisingly, the exact same thing used on edge 2, 4. And come down to 3, 2. There's nothing used on 3, 2. There's nothing used on 4, 5, 5, 6, and 5, 7. Basically the same as what we had up above on 2, 3, and 3 and 2, 4. Although again, remember that I've renamed that variable as I2 to make sure that we don't get confused about thinking that it's the same thing as what was in the original I. Great, nothing in 6, 5. So there we go. Now we've got our def use tables all set up. That was definitely the easy part, right? Not too hard. We'd already done the hard part when we annotated the graph. All we really did here was copy it off the graph into our tables. So we briefly mentioned last week several different data flow criteria that we could use. And the first one, and the simplest one, requires that we cover at least one path from every def to at least one use of that def. So this is all defs coverage. So for every def of a variable, we have to test a path that goes from that def to some use of that def, any use of that def. We can also have all uses coverage. All uses coverage, we've turned the dial up a little bit. Now we're saying that our test requirements contain a path from every def of a variable to every use of that variable, for every use of that def. So instead of, in the previous one, saying I have to get from a def to at least one use, now I have to get from a def to every use of that def along some path. But now I can turn the dial up even further. And I want to make sure, I'll go over this because I want to make sure that you get the difference between these two, because it's a little bit subtle. Here I have all DU paths coverage. This is even more complete. I have to get from every def to every use of that def, but I have to get there on every possible path. So I'm going to back up again a little bit here. All defs, I have to get from a def to one use of that def. All uses, I have to get from a def to all uses of that def, but I only need to get to each use using some one path. All DU paths, I have to get from a def to every use of that def along every possible path that can get me there. So that's the difference between them. All right, so let's start looking at our DU pairs, right? We understand we need to have some DU pairs, have to identify all the DU pairs, to in turn identify all the DU paths, to in turn figure out which of those paths satisfy those three criteria. So we'll make up a table of our DU pairs. And again, this is the overall table, and I'm going to go through these one line at a time so that we can see the control flow graph. Oh, excuse me. We're not using the control flow graph anymore. We're using the tables that we just built. So what are the DU pairs for numbers? This is places where I go from defs of numbers to uses of numbers. What DU pairs do we see here? All right, I see 1, 3 in the chat, 1, 3, 1, 4, and 1, 6. So let's take a look at that. 1 gets deft in 1, gets used in 3, gets deft in 1, gets used in 4, gets deft in 1, gets used in 6. Doesn't get deft anywhere else, doesn't get used anywhere else. So that looks good. What about 1, 1? That sounded like a trick question. It's because it is. Why not 1, 1? All right, so 1, 1 isn't a DU pair because if we go back to the code, numbers was being deft as an input argument and then used after that within the same node. So that's considered a local use, a def and then a use in the same node. That's a local use. From the perspective of this work for DU pairs and DU paths, we can ignore it. All right, how about length? Defs and uses for length. Where are we defing length? Thought I heard a voice, but it was very, very faint.
You're only deafening length at 1, right?
Now I'm definitely hearing a voice, but it's still very, very faint. I'm afraid I can't make you out. All right, so 1, 4 and 1, 7. So we're defing in 1, Yeah, length. We're defing in 1, we're using in 4. We're defing in 1, we're using in 7. There it is. Okay, so we're not using it in any other node, but we are using it in edges too. So we have to make sure that we include that. So that's going to look like this. We've got the 1, 4, we've got the 1, 7, right? So everybody who said that was correct. But we also have 1 to 2, 3, and 1 to 2, 4, and 1 to 5, 6, and 1 to 5, 7. Okay, that was you, Kyle. Yeah, it was like a tiny, tiny little voice way far away. So I guess you're stuck typing today. So we don't want to forget the edges when we're looking at DU pairs. All right, let's move on to MED or MED, whatever you'd like to call it. What are our DU pairs for this? Okay, deft in 4. Used in, yeah, looks like only 7. Doesn't seem to appear anywhere else. Doesn't seem to appear in any of the edges. So 4, 7 seems like the right answer. Good. How about var? All right, I see a 7, 7, if any. Okay, the if any is a good one. All right, we're seeing 7, 7. It's deft in 7, it's used in 7. That means that we should probably go back and check the original source code and see how was this set up? Did it get deft and then used in the same node? Because if it did, then that's a local use and we don't need it. And in fact, 7, 7, but when we look at the code, we see that we deft it and then we used it all in the same node. So 7, 7 is not a DU pair with respect to variable var. Great, thank you. Okay, how about SD? SD is kind of looking the same here, right? Deft in 7, used in 7, but it's a local use. Means, where are we, what are we doing with means? Four, 7, 4, 6. Yeah, both of those look right. 4, 6 and 4, 7, both. Yep, great. Sum, you guys are really getting the hang of this now. So sum is maybe a little bit interesting here. Slightly more complex than some of our other variables. So remember, here we're talking about DU pairs. DU pairs do not need to be def clear. It's just a def and a use we could potentially get to. So 3, 4, deft in 3, used in 4. Yep. And what about 3, 3? And turns out there are actually some other things here with sum, because sum is also deft up in node 1. So sum gets deft in node 1, and then it gets redeft in node 3, but it gets redeft in terms of itself in node 3. So it's actually, this def is then used here in making the def. So the use comes before the def and it's in a loop. Therefore, 3, 3 is a DU pair. All right, var sum, deft in 4 and in 6, used in 6 and in 7. And 6, 6 is legitimate because var sum is deft based on its value, right? So we're using the old var sum when we redef it. So that, and it is in a loop, so that's a legitimate DU pair. And then I gets used lots of places, right? I gets deft in 1 and then deft in 3. In 1 is where we initialize it to 0, and in 3 is where we increment it. And then it gets used in 3 when we do the increment. So we have 1, 3, but then we also have from 1 to the decisions in 2, 4, and 2, 3, and 2, 4. So we have 1 to 2, 3, 1 to 2, 4, 1 to 3, and then the redef, the increment at 3, gets used in these decisions as well. So we have 3 to 2, 3, 3 to 2, 4, and then 3 to 3, which is a legitimate def because we're redefining it in terms of itself. I2 is going to look just the same, different node numbers, but exactly the same pattern because it's the same piece of code, basically, right? It's a copy of the same loop. So that leaves us with all of these DU pairs. And here I chose to list 7, 7, but cross it out. I mean, I suppose I could have listed 1, 1 and crossed it out too. I just didn't happen to do that. So given our DU pairs, next we want to figure out what are the DU paths. So what's the difference between a DU pair and a DU path? Anybody can anybody tell me that? Def clear, there you go. So a DU pair is just 2 nodes, a def and a use. A DU path is a def clear path from a def to a use. So not only do we care about it being def clear, but now it's a path. So we have any other intervening nodes as well. Good, thank you. All right, so for this, we're going to have to go back to the flow chart, right? To the control flow graph, excuse me. So if we look at DU pair 1, 3, what's the DU path for that? All right, 1, 2, 3. Good. Is there any other DU? Is there any other DU path from 1 to 3? And the answer is kind of no. There's no other way to get there. So 1, 2, 3. All right, and now we have 1 to 4. What is the DU path for the DU pair 1, 4? 1, 2, 4. Okay, that looks good. What about 1 to 6? What's the DU path for numbers for 1 to 6 for the 1, 6 DU pair? 1, 2, 4, 5, 6 looks good. 1, 2, 4, 5, 6. And we can do the same for length. We'll go through length and then I think we'll skip over the others. You guys are really getting the hang of this. So what's if my DU pair is 1 and 2, 3, that's node 1 to edge 2, 3, what's my DU path? Now here for the DU path, we're going to be listing nodes, right? We don't list edges in the DU path. They're kind of implied by the ordering of the nodes. So what's the path that will satisfy the DU pair 1, 2, 3? All right, 1, 2, 3, yes. Not that hard, right? Pretty straightforward. 1, 2, 4 is similarly pretty straightforward. 1, 4, what's our DU path for 1, 4? 1, 2, 4, great. How about the DU path for 1 to node 5, 6? One, 2, 4, 5, 6. That looks good. And we've got 1 to 5, 7, and then 1 to 7. Now it just happens to turn out that those are the same DU paths, so that's fine. Great. We can work our way through the rest of these variables. I'm not going to continue to beat this on a 1-by-1 basis, but 4, 7, right? 4, 5, 7, pretty straightforward. We'll work our way. Through this. All right, question in the chat. Does it need to be the shortest path for a DU path? No. A DU path can be any path, right? Any path from this DU pair, from this node. Back up a little. A DU path is any path that will satisfy this DU pair. So 4, 6, I really don't have a choice. It's going to be 4, 5, 6, right? It couldn't be anything longer. It couldn't be anything else. It could potentially be 4, 5, 6, 5, 6, but a DU path is a simple path. And so 4, 5, 6, 5, 6 is not a simple path because 5 and 6 both appear twice. So that's why that would not appear here, and only 4, 5, 6 would. 4, 5, 7 straightforward. Looking at sum, right? We could fill all those in. We can do var sum. I'm going to breeze through these. As always, this is posted online for you to review in more detail later if you'd like. Okay, the DU pairs are a little complicated. The DU paths aren't really that complicated. To get from node 1 to edge 2, 3, 1, 2, 3. From node 1 to edge 2, 4, again, 1, 2, 4. Right, so we can work our way through all of those. I2 is going to look remarkably similar, right? It's the same structure, that piece of the graph. So there we go. That takes us to all of our DU paths. We've now accumulated a list of all of the DU paths.
Can we go back for 1 second?
Sure. How far?
That's good. For the ones
Okay.
that are like 6, 6, which is valid because it was updated, it was redefed based on its use after the fact.
Yes.
Does that one always have to go back? Like you always have to go back to the one it looped from. So 6, 5, 6 at the bottom.
Well, if I want to satisfy 6, 6 as a simple path, then if this is my graph, how do I get from 6 to 6? Really, I can only go through 5.
So it's not just that you stay, I guess, right? You
No.
have to redef, use. Okay.
Yeah, because in this case, this was a DU pair because the def happened after the use, right? So really what happened here is that it was redefed in terms of itself. It was like I equals I plus 1. So there's a use because we have to evaluate the R value first. So we're using the old value of I, and then we're setting a new value of I. And if I want to take that new value of I and use it again in the same node, I have to go back around the loop again.
Got it. Okay, that makes sense. Thank you.
All right, thank you. Appreciate the question.
I have another question for
Sure.
that. So for the numbers, you opt out the 1, 1 because it's local use, but for assume that you added 6, 6, right? So when you fill out the tables, I'm asking is if we doing an exam or something, if we rely on the table because as you do the exam under the example, you use the table node and def and use to build up this table. So without like going back, how would you know that this is 1, 1 is not valid? No.
When you're building your DU pairs, let me go back a bunch of slides to get to where we're working on DU pairs. When you're building your DU pairs, this is where you would say, oh, I'm defing I in node 3 and I'm using I in node 3. This is where I would need to go back to my control flow diagram and say, okay, what are the rules? If it's a def then a use in the same node, then that's not a DU pair. So it's here when I'm kind of putting this DU pair list together. Okay, numbers is deft and used. Is that a DU pair? Oh, the def comes before the use? Okay, no, it's not a DU pair. And so I wouldn't include that. Or like I did with several of these, I included it for the sake of discussion and then I crossed it out just so that we'd be sure we talked about it. But this is the point where you'd say, oh, okay, I have a def and a use in the same place. Is that really a DU pair or is it a local use? Well, I can't tell from here. I have to go back and look at the control flow graph in order to make that decision.
I see. Thank you.
All right, you're welcome. All right, so yes, get caught up back where we were. We did all the DU paths. Okay, that gave us our new list. We've got our variables, all the DU pairs, all of the DU paths that correspond to those DU pairs. Now, if we take these DU paths and we look at them all, we've got a whole bunch of them, 32 of them. But it turns out only 10 of them are actually unique, right? Because 1, 2, 3 appears here for numbers, but 1, 2, 3 also appears for length, and it appears for sum, and it appears for I, right? So we have far fewer unique DU paths than are actually represented in this table. So we'll go through that and we'll sort it and we'll take out the duplicates and we'll end up with these 10 unique paths. And these have some interesting properties. So these 3 paths don't execute a loop. These paths skip over a loop, right? If we went back to our control flow diagram and said, okay, what does 1, 2, 4 do? What does 4, 5, 7 do? Oh, those are the paths that don't execute the loop. And then we have 5 of these 10 that execute the loop at least once. So 1, 2, 3, that enters the first loop. 4, 5, 6 enters the second loop. And then we have 2 of them that execute a loop at least twice, right? This is 3, 2, 3. The body of the loop going out of the loop, going back into the loop again. So this is just interesting to note, right? These are the kinds of cases that this data flow analysis is bringing to our attention and is putting into our set of test requirements. So this is kind of already starting to feel like a pretty thorough set of test requirements, right? There's a lot of different things I have to do with this control flow graph to satisfy these DU paths. Okay, so next, for all defs coverage, we have to cover at least one DU path from each def to one use, right? So we can pick our variable, we can pick our def, and we have to cover at least one path. Here I have kind of arbitrarily said, well, okay, for numbers deft at node 1, I'm going to choose path 1, 2, 3. Why 1, 2, 3? Well, because I can use 1, 2, 3 to satisfy a number of other cases too. So it seems like a good one to pick. I wouldn't want to come down here for length and say, well, I'll use 1, 2, 4, 5, 6 because I already have 1, 2, 3. I may as well just apply that same test, right? Because I can now write one test and satisfy both numbers and length. And I should try to satisfy my test requirements in as few tests as I can. So here I've highlighted, perhaps somewhat arbitrarily, DU paths that will satisfy all defs coverage, right? So for every def, we're going to some use. Not every use, just some use. And as I said, I want to maximize our coverage for each path that I pick. I want to maximize how much they're being reused between variables. You could make other choices, right? You could say, well, 1, 2, 4, that'll also get me length, and it'll also get me sum, and it'll also get me I. Great. You could make other choices about your paths. These are not the correct choices. They're only examples of choices. For all uses, I have to go from a def to every use of that def, but I have to go there by every possible path. So I have to first go, sorry, I'm getting ahead of myself and I misspoke. This is all uses. I have to go from every def to every use of that def. So I have to go from 1 to 3, and from 1 to 4, and from 1 to 6. And that's why now in this particular graph, I now have to use all of these DU pairs. If I wanted to do all DU pairs coverage, all DU paths coverage, excuse me, then I would have to go from every def to every use by every possible path. But it turns out in this graph, that doesn't add anything, right? There are no more paths, no more DU paths to pick from. So in this graph, all uses and all DU paths, the solution is the same. All right, so let's now work on taking, we're going to do all uses, right, the simpler one. Let's work on taking our DU paths and turning it into test paths. And then thinking about what are the particular test input values that I would use to cause that test path to be executed. All right, so we're actually taking two steps here. We're going to say, okay, 1, 2, 3. Well, I know 1, 2, 3 is not a test path because it doesn't end on a terminal node. So I'm going to need to make some test path that covers 1, 2, 3. And then I can do that for all the rest of these as well. Then we're going to come back in a separate step and say, well, now that I have some test path, what are the input values that I would use in order to make that path of execution happen? All right, so we're going to do test paths first. So here we are back to our, looking back to our control flow graph annotated with source so that we can see what's going on. And if I want to execute DU path 1, 2, 3, what is a test path that I could execute? Okay, I see 1, 2, 3, 4, 5, 6, but I think you left something out there, 4, 5, 7, but you did leave something out there because if I go 1, 2, 3, I can't go to 4. I have to go 1, 2, 3 back to 2 and then 4, 5, 7. So I forgot the 2. Yep, no problem. 1, 2, 3, 4, 5, 7. Seeing a couple of those come up. That seems like a pretty reasonable thing to do. 1, 2, 3, 4, 5, 7. Great. Now, what test values would I use in order to execute that? So I have to go around the loop exactly once. So what would numbers have to be? Or what could numbers, the numbers array, be in order to make me go around the loop exactly once? An array with one element, or greater than or equal to one element. Well, greater than one element wouldn't get me this test path. If I had greater than one element, I'd go 1, 2, 3, 2, 3 again and continue around that loop for as many elements as I had. But if I have exactly one element, then yes, I'll go 1, 2, 3, 2, 4. So that sounds good, but wait. If I have one element in numbers, then how do I go 4, 5, 7? Because this is another loop based on the number, right, iterating over the elements of the numbers array. So it turns out that path is infeasible. I can't go around the loop up here for every element of numbers and then not go around the loop down here for every element of numbers, because the loops are essentially the same logic. The way this code is written, I have to execute the first loop and the same loop exactly the same number of times. So that's infeasible, right? The loops are coupled by the same input. But I could do this test path. I could do 1, 2, 3, 2, 4, 5, 6, 5, 6. Now I've gone around both of the loops exactly once. That is feasible. So what would my test input numbers look like? Well, going back to the previous answer, yeah, an array with one element. So for example, that. So does that satisfy anything else? I've written myself a test path. Here's a test path that I can execute. Does this test path satisfy any other DU paths that I know I need to satisfy? Another way of asking that question is, are any of these DU paths a proper subpath of the test path that I just made? Because if they are, then this test path will also satisfy those DU paths too. 1, 2, 4, 5, 7. Oh, does it? Well, it would satisfy that with a side trip or maybe a detour, but right now I'm really looking for things that will directly tour that. And 1, 2, 4, 5, 7 is not directly in here. But 4, 5, 6 is, 6, 5, 7 is, and maybe there are some other answers in here that are scrolling off. Yeah, so good. Now you're on the right track. We've actually satisfied a couple of other things. We've satisfied 4, 5, 6. We've satisfied 3, 2, 4. Yep, that was in the chat too. 6, 5, 7. Good. So collectively, you got them all. You found all the other subpaths that we satisfy with that test path. No need to write 4 tests if we can write 1 test. So now let's move on to the next one. 1, 2, 4. What's a test path that will satisfy 1, 2, 4? 1, 2, 4, 5, 7. Yes, 1, 2, 4, 5, 7. And our gut feel is that seems like it would be a feasible test path because it executes both loops 0 times. So 1, 2, 4, 5, 7, that looks good. And I don't even have to ask questions anymore. I just get answers. This is terrific. Empty array, right? So if my array has no elements in it, then I will execute 1, 2, 4, 5, 7. Nicely done. Turns out this actually finds a fault because the way this code is written, if I execute this with an empty array, we come down here, length is 0. I divide 0 by 2. That gives me 0. And then I dereference numbers sub 0. Well, numbers is empty. It doesn't have a 0th element. So that will cause an array out of bounds exception. So congratulations, you found a fault in the code. And it really wasn't obvious by looking at it, was it? At least I didn't think so. All right, so we've satisfied that. With that test path, does this test path satisfy any other test paths? 4, 5, 7. Yep, satisfies 4, 5, 7. Also satisfies 1, 2, 4, 5, 7, which happens to be the entire the entire DU path. Nevertheless, yes, good. 1, 2, 4, 5, 7 in the chat. Great. So we've written our second test and we've knocked off 3 more. We'll pick our next one that hasn't been satisfied yet. 1, 2, 4, 5, 6. And what's a test path that will satisfy 1, 2, 4, 5, 6? Okay, I'm seeing 1, 2, 4, 5, 6, 5, 7. 1, 2, 4, 5, 6, 5, 7. 1, 2, 4, 5, 6, 5, 7. Great. That looks like a very reasonable test path to satisfy this. What are our test inputs? Yeah, not feasible, exactly. Because this, much like the last one, but now reversed, we're executing the first loop 0 times, but we're executing the second loop 1 time. And the loops are still coupled. They're iterating over the same array. So this is not feasible. What could we do instead that satisfies 1, 2, 4, 5, 6? Is there some alternate test path we could use? 1, 2, 3, 2, 4, 5, 6, 5, 7. Except that actually doesn't satisfy this directly. It does satisfy it with a side trip or a detour. But that's not what we're trying to achieve here. So if we set aside side trips and detours, although I'm glad you're thinking in those terms, turns out that's just not feasible at all. So setting aside side trips and detours and requiring us to do it directly, we would have to say that DU path is infeasible in its entirety. Now, we could, as you're suggesting, say, well, I couldn't do it directly, but I could do it with a side trip, and maybe that's better than not doing it at all. So you could replace it with some feasible test path. For the moment, we're going to mark that one as infeasible, and we're going to kick it to the curb. Now we've got our next DU path on our list, right? Are we? Yes. Okay, right. We're down to here. So 323 is the next DU path on our list. What test path will satisfy that? 1, 2, 3, 2, 3. 1, 2, 3, 2, 3, 2, 4, 5, 6, 5, 6, 5, 7. That sounds good. I got another one here. 1, 2, 3, 2, 3, 4, 5, 7, which is a path on the graph. It's syntactically feasible on the graph, but we know now because the loops are coupled, I have to go around both loops the same amount of time. So 1, 2, 3, 2, 3, 4, 5, 7 is not feasible because I go around the first loop twice and the second loop not at all. But the earlier one, I'm not going to try to repeat it. It's too many numbers. We ran around the first loop twice. We ran around the second loop twice. That is a feasible test path. So 1, 2, 3, 2, 3, 2, 4, 5, 6, 5, 6, 5, 7. Ugh. What would give us, what kind of input, what is an example test input that would execute this path? Yeah, numbers is 2 elements, any 2 elements, right? 2, 3 in my case, 1, 2 in another example in the chat. Great. Now we're back here. We've got this nice long test path. We only have one thing left that isn't satisfied yet. Did we satisfy it? Does this test path satisfy anything else? It satisfies 323. Does it satisfy 6562 or 656 also? Yes, it does. So boom, there we go. So now if we look at what we ended up with, we actually satisfied all uses with 3 tests and 1 infeasible requirement. Again, if we wanted to say, well, I'd like to satisfy this best effort, right? I'd like to satisfy this with a side trip if I can, then maybe we already have something that satisfies it with the side trip. I kind of expect that we do. Or maybe I'll need a 4th test case, but I think in this case, we've already got what we want. Kyle makes the very interesting argument here in the chat. Totally agree with you, Kyle. This is a good argument for refactoring the code to have only 1 loop in it. Totally agree. That would really make our testing so much simpler and would eliminate all this nonsense about infeasible paths. All right, that takes us to the end of our exercise. So let's go ahead and take a break now. We'll do 15 minutes. That'll bring us back at 6:20. When we get back at 6:20, we'll break up into our groups and we will do much simpler things than this. So this was a great exercise because it's nice and in detail. Thank you all for your, for your contributions to this. I really do appreciate it. It's way more interesting that way than me just reading through it all. Hopefully more interesting for all of us. The group activity after we get back from break will be simpler than this because there's just not enough time to do this again. All right, see you back here at 6:20. All right, next up, class activities as usual. All right, here you've got a graph definition. This is posted so you can easily grab it, which you'll probably want to, so that you have the graph definition, or I'll leave it here for a moment so you can just take a screenshot of it or whatever you'd like to do. But here's our graph. Nodes, initial nodes, final nodes, edges, and defs. So what is this telling us? Okay. X is deft at 1 and 4, and X is used at 3 and 5 and 7. That's what this notation means. All right, so here's what we're going to do, and who's going to be presenting, what groups anyway. So first, draw the graph. Draw the graph, annotate the graph with the defs and uses as described on the previous sheet. Then list all the DU paths with respect to X. Remember that a DU path is any syntactically valid path through the graph that goes from a def of a variable to a use of that variable. DU paths, back up. DU paths, I totally was going to totally misspeak. DU paths are a path from a def to a use that's def clear. Now, DU paths can be subpaths of other DU paths. If I had a def use, then that def use is a DU path, and the def use is a DU path also. They're actually two separate DU paths. One's a subset of the other. And then, given these particular test paths, these two test paths, which ones tour the required DU paths directly, with a detour, or with a side trip? And then list a minimal test set. And again, this is what I was talking about earlier that I wanted to come back to. A minimal test set is one in which I can't remove any of the test cases or the test paths and still satisfy the requirement. So they're non-redundant. There are no extra ones in there. It does not mean the smallest possible set, although that's nice too, but that's not what minimal means. That's what minimum is, the smallest possible test set. Minimal is a test set that has no redundancy. So list a minimal test set that satisfies all defs coverage. That is, from every def to one use. And then list a minimal test set that satisfies all DU paths coverage, from every def to every use along every possible path. All right, we good to go? Any questions before we do? All right, I'm going to make this 20 minutes as soon as I find my groups page here, my breakout rooms. We'll make this 20 minutes. That'll give us time to outbrief and at least time to get started on the second part of this. If we don't finish the second part of this by 7, I'm not too worried. All right, see y'all in your rooms then. All right, so welcome back. I'm not sure if anybody quite finished, but that's okay. We'll just go through what we've got. So we're going to start with the Hufflepuffs tonight. Now, before we do this, I did send out a broadcast message. I don't really know how that works, or even if that works, or who saw it. But you know, especially with the change in grading strategy that makes presenting a 2-pointer for participation points. If you haven't presented before, or haven't presented a lot, or you know, just need to start working on your points at this point in the semester, consider presenting for your group, because it's a great way to make some points. So that said, let's go over to the Hufflepuffs, and we'd like to see your graph that you drew and how you annotated it with your defs and uses. All right, let's see the graph. Great.
Sorry, I was on mute. Can you guys see my screen?
Yes.
Cool. Yeah, so we just built this graph. Basically, we defined x, or we're defining it, so x equals value. It could be anything. And then we listed the use type above the node and below it here. And then we defined it again. and then we just label the use case underneath the node here.
Okay, good. So where you have, x equals value and x equals value 2, you don't actually need that. You can just say def x, because
I see.
it doesn't really matter what we're setting it to. So it's fine to just say def of x.
Okay.
All right, good job, thank you. All right, let's go over to the Raven clause.
Yeah, let me share my screen. So we have come with this du pairs, like we can see x is defined at first node and it is used at third node. So we can say 1, 3 is one pair, and as like that, it's same thing at it's defined at fourth node and used at fifth node. So 4, 5 is the one. Same
Mhm.
for like 1, 6 along this path, 4, 6, 4, 3, and 1, 5. And by using these du pairs, we have come up with this path. So for 1, 3, the path is 1, 2, 3. And for 4, 5, the path is only going to be the 4, 5. That is defined at 4 and used at 5. So path is going to be only 4, 5. And for 1, 6, path is going to be the 1, 2, 6, 1, 2, 6. And same for other pairs as one. Yeah.
Okay. All right, that looks great. So the approach that you obviously took, much like we did in the collaborative exercise, you went through, you identified all the DU pairs first, and then you went back and found, okay, what paths can I make from the DU pairs? And your set of DU paths exactly matches my set of DU paths. So nicely done.
Okay, yeah, thank you, Professor.
You could also say, your group or some other group, whatever, you could say, well, this is really pretty simple. It's a pretty simple graph. I don't really need to draw out all the DU pairs first. I can just look at the graph and come up with the DU paths. That's fine too. But, I don't think you can go wrong doing it the way that you did it. It's a little more methodical and maybe helps prevent you from getting into any mistakes. So nice job. And also I note that you were very effective at realizing that DU paths had to be simple paths. So none of your DU paths have any loops. So great job. Thanks.
Yeah, thank you.
All right. So next we're going to see what DU paths are toured by each test path. Now, I'm not sure how far everybody got. So, don't be too embarrassed by saying, at some point, hey, we didn't get to that. That's okay. Muggles, did you get to this part and were you able to compare your the given test paths against your DU paths?
Yes, we did. Does anyone else in the group want to share? We didn't talk about who was going to share.
Yeah, I had meant to say that before I sent you all off, and then I kind of got caught up and forgot about mentioning that.
Okay, I'll go ahead if any of you want to chime in, please feel free. So we labeled or can you guys see my screen?
Yes.
We labeled our DU paths with letters so we could identify them more easily. And we said that this T1 is B, C, and A with a detour. So B is 1, 2, 3. So here we have 1, 2, 3. And we end with the terminal node. C is 1, 2, 3, 5, 1, 2, 3, 5. And then A with a detour. So 1, 2, 6, 1, 2, detour 6.
Okay. All right. And then T2.
T2, we have B again. So 1, 2, 3. D, which is 4, 5. F, which is 4, 5, 2, 6. And A again with the detour. We did not find E in these.
E, 4, 5, 2, 3. Okay, good. What about C?
C is in the first one.
C is in the first one.
1, 2, 3, 5.
And it's
Oh,
actually
detour.
Yeah, it's actually in there also with the detour. Yeah, great job. Good, thank you. I'm just going to share my screen for just a moment here. Get the right one. There we go. There's my graph, which isn't that important, but this was just the way that I notated this. You know, the way you did it is fine, makes total sense, works out to be the same thing. I just kind of built this table with rows and columns to, you know, to make it easier to see what was going on.
We can't see your screen.
Can't see my screen.
There
How
it
about
is.
now? Okay.
Better.
Great. Sorry about that. So anyway, I just built this little table. Same test paths as yours, same results as yours, just a little bit of a different annotation. So just wanted to show that. All right, so next up we have the minimal test set, right? What's the test set that satisfies all defs coverage? So we're up to the Gryffindors next. I know that this is getting pretty far. Gryffindors, did you get to this point?
I can go if no one wants to go.
So we did not get to that, Professor.
Okay.
I have some answer for that as well. So the path that I have, we didn't have time to cover, but when I look at the graph, I just quickly have a path here. Is the path is 1, 2, 3, 4, 5, and back to 2, and then 6. So we have depth in node 1 and node 4, and then use in 5, 3, and 6.
That is exactly correct. Good job. All right, thank you. And then last, we were looking at all DU paths coverage for this. We had an empty group in Slytherin today. So we're going to hook back around to, I guess I'll say, any volunteers rather than putting anybody on the spot. I don't know if anyone got to this. Any volunteers for all DU paths coverage using direct touring? All right, nobody quite got that far. That's fine. So then our next thing that we had here, let's see. Next graph coverage exercise. Let me see if I can get my screen shared correctly this time. All right, so this exercise was to take this code to draw a control flow graph of this code. I am looking at the right thing. Yep, draw a control flow diagram of this code and then look at node coverage, edge pair coverage, edge pair coverage, and prime path coverage. So we are not going to be able to do that tonight. We're 5 to 7. Like I said, technically we're 7:10. I don't like to go that late. We clearly don't have enough time to dive into this. But I will post the version with the answers. That will be up right after class. I'd encourage you to at least look through it, and you might want to actually do this on your own and then compare your results against the results that I post. Because as usual, this week's quiz is going to be largely based on what we were doing tonight, either with the diffuse stuff or with generating a graph out of code, or maybe some of both. I'm going to remain mysterious for the moment. So do make sure you've got a handle on this as well before you start the quiz. Make sure you're feeling comfortable with taking code and structures in code like while loops and if statements and translating them into control flow graphs. All right, so I think we'll call it at that. Any questions or discussion that we want to have before we break for tonight?
Yes, I have a quick question here, Doctor.
Sure.
So this snip code that we have here that have a return the result, and then we also have the exception, illegal argument exception. So assuming that there's going to be two final nodes for this, at least two. I mean, now I see the no pointer, so it's going to be like 3 final nodes.
Exactly, because we have a throw in here, and that throw isn't matched up with any catch, right? So we're not having a transfer of control within this function. So this throw, because it's not caught anywhere inside here, would just be a terminal node. You are exactly right.
Yes. Thank you, Doctor.
All right. Anything else tonight? I lost my chat screen. Let me pull that up and just make sure that we're
So you recommended we do
good here.
exercise 3 on our own?
You know, it wouldn't hurt.
Did we
You
do
know,
exercise 2 already? Or was like trying to...
Yeah, this was just, it was, it's listed as exercise 4 and exercise 3 because I think that's the numbers in this chapter of the text that it came out of.
Oh,
So yeah, sorry, that's a little confusing. It wasn't 1 and 2 sequentially here for
okay, mate.
for our work.
Paying attention.
Yeah. Right. When I wasn't looking, they skipped through a whole exercise without me. Super fast. Yeah. Nope. Sorry about that. Sorry for the confusion. All right. Well, we'll leave it at that then. Let you out a couple minutes early, although now it's 6:59, so it's not really all that early after all. Again, I'd really like to thank you for your, for all of your participation tonight. This is really more fun and kind of more rewarding for all of us when it's in person, but that's the breaks. But thanks for your help and for playing along tonight. And let's see, assignment. This current assignment is due tonight. The next assignment comes out due in 3 weeks. Otherwise, I don't think there's much to report. Next week is class as usual on Monday as usual. I do want to remind you of the discussion that I started about the difference between annotating a decision on the node versus on the branches. And now that let me throw you a little hint. Now that you've gotten some experience in def use and DU pairs and DU paths, think about whether there's now a difference between those two representations. And let's talk about that in Blackboard. And with that, I bid you good night, and I'll see you next week.